So we'll be solving February-March 2022, paper 4, variant 2. So the first question says the point P in figure 1.1 represents a point mass. On figure 1.1, draw lines to represent the gravitational field around P. Because it's a point mass, it will have a gravitational field, and the gravitational field would be radial, pointing inwards towards the mass, because that is the direction of force on any mass, any other mass placed close to it. So this is how we'll draw it. You'll have gravitational field lines, radial, and they should all point inwards towards the mass. You can draw more field lines if you want, but at least 4 field lines are necessary. Part B says, a moon is in circular orbit around a planet. Explain why the path of the moon is circular. Why is it that the path is circular? Because for this moon going around in a circular orbit, it needs a force, and that force is known as centripetal force. This centripetal force is provided by this necessary centripetal force is provided by the gravitational force. So it has a centripetal force provided by the gravitational force. The force, this centripetal force or the gravitational force, is perpendicular to its velocity, to the velocity of the moon, thus keeping it in circular motion. Part C of the question says, many moons are in circular orbit about a planet. The angular velocity of a moon is omega when the orbit of the moon has a radius r about the planet. Figure 1.2 shows the variation with r cube with 1 upon omega squared for these moons. Show that the mass m of the planet is given by the expression m is equals to gradient over g, where g is the gravitational constant. Now, how do you get this equation? We basically need an equation that links the radius with the omega and has mass, because that is the only way we'll get gradient. Now, we've already said that for this moon in circular motion, the centripetal force is provided by the gravitational force. Or I can say mr omega squared, the centripetal force, is equals to g m over r squared. This lowercase m cancels out with this lowercase m, which is basically the mass of the moon orbiting the planet. We can rearrange this equation, and that would give us m is equals to r cube omega squared upon g. Now let's see what the gradient of this line is. If you look at the gradient of the line, gradient is basically y2 minus y1. Gradient is y2 minus y1 over x2 minus x1, or y over x, or rise over run. Change in y over change in x. So r cube divided by 1 upon omega squared, this being our y value upon this being our x value, that is the gradient of the graph, which can be written as g is equals to r cube omega squared. So this thing here, this numerator here is actually, the gradient. So we'll replace this with the gradient. M is equals to gradient over g, over capital G, the gravitational constant. This here is gradient. Don't mistake this for g, the constant, gravitational constant. Use figure 1.2 an expression in C1 to show that the mass m of the planet is 1 into 10 raised to the power 26 kilograms. So we have the equation m is equals to gradient upon g. What we need to do is find out the gradient. What is the gradient of the graph? M is equals to gradient over g. The gradient of the graph, let's do this here separately. The gradient of the graph is change in y over change in x. So the gradient is this value, which is 4.1 into 10 raised to the power 23. Always have a look on the y-axis, upon 6 into 10 raised to the power 7, and the x-axis. Always check the axis of the graph. So 4.1 into 10 to the power 23 upon 6.1, 6 into 10 to the power 7, that is the gradient. 4.1 into 10 raised to the power 23 upon 6 into 10 raised to the power 7, which is equals to 6.83 into 10 raised to the power 15. Let's substitute this here. Divide this by the gravitational constant, which is 6.67 into 10 raised to the power minus 11. And that gives us the mass of the planet M, which is equals to 1.0 into 10 raised to the power 26 kilograms, hence shown. Part 3 says, determine the speed of a moon in orbit around the planet with the orbital radius of 1.2 into 10 to the power 8 meters. They've given us the radius. We know the mass of the planet. They want us to find the speed of the moon. Now, you may remember the formula that v squared is equal to gm over r, or v is equal to under root gm over r. Or if you don't, you know that gmm over r squared, which is the gravitational force, is equals to the centripetal force mv squared over r. We're using a different formula, mv squared over r as opposed to mr omega squared. Rearranging it gives us v is equals to under root gm over r. Now, g is 6.67 into 10 raised to the power minus 11. The mass is 1.0 into 10 raised to the power 26 kilograms upon r, which is 1.2 into 10 raised to the power 8 meters. This will give us the speed of the planet, the speed of the moon, which is 7,500 meters per second. Question number 2 of the paper says, a fixed mass of an ideal gas has a volume V and a pressure P. The gas undergoes a cycle of changes x to y, y to z, and z to x, as shown in figure 2.1. Table 2.1 shows data for P, V, and T for the gas at points x, y, and z. State the change in the internal energy delta U for one complete cycle x, y, z, x. So for the gas that is initially at this pressure and volume, if it undergoes one complete cycle, what is the change in internal energy? There is no change in internal energy, because the gas ends up with this at the same pressure. When it returns back to x, it ends up at the same pressure, same volume, and same temperature as it was at its starting position. So no change in internal energy. How many joules? 0 joules. Part B says, calculate the amount N of gas, the number of moles of gas. We've got the pressure at x, we've got the volume at x, and we've got the temperature. We can use PV is equals to nRT. The pressure is 1.5 into 10 raised to the power 5 pascals. The volume is 4.2 into 10 raised to the power minus 3 meter cube. N is our unknown, R the constant 8.31, and T is 540 Kelvin. Rearranging and solving for N would give us 0.14 mole. C says, complete table 2.1, use the space below for any working. So complete the table. Now, we know that for an ideal gas, P1, V1 over T1 is equals to P2 V2 over T2. We've got P1, let's say this is 1, let's say this is 2, let's say this is 3, which is equals to P3 V3 over T3. PV over T is a constant because that's equal to NR, and the number of moles are constant, and so is R are constant. So using this data for X and equating it to this data for Z, we can find out V. So 1.5 into 4.2 upon 540 is equals to 5.1 times V upon 782. Now the reason I haven't included these orders 10 to the power 5 and 10 to the power minus 3 is because they'll cancel out. So there's no point in doing it, but if you do it, that's not an issue. The answer that we get for V is 1.8, and we already know that this will have a power of, this will be in multiples of 10 to the power minus 3. So this here is 1.8 into 10 raised to the power minus 3. Now let's go back to the diagram and see what they've given here. If you look at the diagram, you'll realize, figure 2.1, that the pressure at X is equal to the pressure at Y. That automatically means that this P should be equal to 1.5 into 10 raised to the power 5 pascals because they are at the same pressure. And the volume at Y is equal to the volume at Z. So this should also be 1.8 into 10 raised to the power minus 3 meters. 2D part 1 says the first law of thermodynamics for a system may be represented by the equation delta U is equals to Q plus W. State with reference to the system what is meant by delta U. Delta U basically means the increase in internal energy. Increase in internal energy. Q is the thermal energy supplied to the system. W is the work done on the system. D part 2 says, explain how the first law of thermodynamics applies to the chain Z to X. Now, the first law is delta U is equal to Q plus W. Let's go back to figure 2.1 and see what happens from Z to X. Now, from Z to X, the volume of the gas increases. The volume starts off at V1 and ends up at this point, V2. What else happens is that from Z to X, the temperature, let's have a look at what happens to the temperature. The temperature goes from 782 to 540 Kelvin. So the volume of the gas increases from 1.8 to 4.2, and the temperature of the gas decreases. If the volume increases, that means there's work done by the gas. So volume increases, which basically means that there's work done by the gas. If the volume would have decreased, we would have said it's work done on the gas. And the temperature has decreased, which means that the internal energy has decreased. Question number 3 says, a small wooden block cuboid of mass m floats in water as shown in figure 3.1. The top face of the block is horizontal and has area A. The density of water is rho. State the names of the two forces acting on the block when it is stationary. A classic AS question. There's a weight that acts in the downward direction, and upthrust is the upward force. So weight and upthrust are the two forces that act on this block when it's stationary. Weight and upthrust. Part B says the block is now displaced downwards as shown in figure 3.2, so that the surface of the water is higher up the block. State and explain the direction of the resultant force acting on the wooden block in this position. Now, in this position, what happens is the weight of the block remains unchanged. It still has the same magnitude. But because it's now submerged to a greater depth, or it's deeper inside the water, the upthrust increases. Hence, there's an upward resultant force because the upthrust is greater than the weight. Part C says the block in B is now released so that it oscillates vertically. The resultant force acting on the block is given by F is equals to minus AG rho x, where G is the gravitational field strength, x is the vertical displacement of the block from the equilibrium position. Explain why the oscillations of the block are simple harmonic. So for any oscillation to be simple harmonic, it follows A is proportional to minus x. In this case, A here is the area, G here is the gravitational field strength, and rho here is the density. All three of these are constant. So F is proportional to minus x. And we know that the force or the resultant force is directly proportional to the acceleration. So this in turn means that A is proportional to negative x. That is why it's in simple harmonic. So we'll write this down, keep it in terms of f and x because that's what the equation is. But this was for your understanding. A, G, rho are constant. Force is proportional to x, or the displacement, and this minus sign here, or this minus sign here, means that they're in opposite direction. F and x are in opposite directions. Part 2 says, show that the angular frequency omega of the oscillations are given by omega is equals to square root A rho G over M. Now, F is equals to minus A G rho X. This is the equation given in the question. And we know that A is equals to minus omega squared x. This is our equation for simple harmonic motion. We can also write this as F is equals to ma, or A is equals to minus A G rho x upon m. If we equate this A with this A, what do we get? We get minus omega squared x is equals to minus A G rho x over m. The x here cancels out with this x. The negative signs cancel out. We get omega is equals to square root A rho G over m, and hence shown that the angular frequency is square root of A rho G over m. Part D says, the block is now placed in a liquid with a greater density. The block is displaced and released so that it oscillates vertically. The variation with displacement x of the acceleration of the block is measured for the first half oscillation as shown in figure 3.3. Explain why the maximum negative displacement of the block is not equal to its maximum positive displacement. Why is it that the two displacements are not equal? This has to do with the liquid being of a greater density. And because the liquid is of a greater density, that basically means that our block now experiences drag forces. And that results in something known as damping. So we'll say that there's damping due to the drag force. Part 2 says the mass of the block is 0.757 kilograms. Use figure 3.3 to determine the decreased delta E in the energy of oscillation for the first half oscillation. How much does the energy decrease by? So the formula for energy, E is equals to half m omega squared x naught squared. The change in energy can be found using half m omega squared x2 squared minus x1 squared. The two different values of x. What are the two different values of x? One of the values of x is this here, minus 0.02. Let's say x2 is equals to minus 0.02. The other value is this value, x1, which is equals to plus 0.016. So we've got the two values of x, we've got the mass. The only problem is omega squared. What's the value for omega squared? Now, as we wrote earlier, that a is equals to minus omega squared x, and this is an acceleration displacement graph. So the gradient of the graph is equals to minus omega squared. The gradient can be found using y2 minus y1 over x2 minus x. So we've got the y values, we've got the x values. Minus 2.3 over 0.02 is equals to minus omega squared, or omega squared is equals to 2.3 over 0.02. So half m mass, which is 0.57, times omega squared, which is 2.3 over 0.02, times x2 squared, which is 0.02 squared, minus x1 squared, which is 0.016 squared. And that gives us the change in energy, which is 4.7 into 10 raised to the power minus 3 joules. Question 4 says, state what is represented by an electric field line. It is the direction of force on a positive charge in an electric field. Part B says 2-point charges P and Q placed 0.12 centimeters apart as shown in figure 4.1. The charge of P is plus 4 nanocoulombs and the charge of Q is minus 7.2 nanocoulombs. Determine the distance from P of point on the line joining the two charges where the electric potential is 0. Where is the electric potential V? 0. Now let's assume V is 0 at this point. It will be somewhere close to P. Now for V being 0 at this point, let's say this distance is x. V0. So this distance obviously would be 0.12 minus x. V at P, V due to P plus V due to Q is 0 at this point. V, the potential, is 1 over 4 pi epsilon naught Q over R. So Vp would be Q, which is 4 nano over 4 pi epsilon naught, 4 pi epsilon naught, where epsilon naught is a constant of known value, times R, which is equals to X plus Vq, which is minus 7.2 nanocoulombs upon 4 pi epsilon naught times the distance from Q to V naught, which is 0.12 minus X, and V naught is 0. The potential at that point is 0. The combined potential due to P and Q is 0 at distance X from P. We'll shift this entire thing to the other side of the equation. That makes it positive. 4 into 10 to the power minus 9 upon 4 pi epsilon naught X is equals to 7.2 into 10 to the power minus 9 upon 4 pi epsilon naught 0.12 minus X. 4 pi epsilon naught cancels out with 4 pi epsilon naught. Cross multiply and we'll solve for X. The value of X that we get is 0.043 meters. This is the distance from P as asked. If they wanted the distance from Q, we'd either do the same thing and then find 0.12 minus X, or we'd replace this distance and write this as X and the other distance as 0.12 minus X. Part 2 says, state and explain without calculation whether the electric field strength is 0 at the same point at which electric potential is 0. Now, before we answer this question, what does electric field strength being 0 mean? Electric field strength being 0 means that the electric force is 0, which basically means that the electric force is 0, which basically means that this is a null point. A null point can only exist if the two charges have the same polarity. So a null point exists between two positive charges. A null point exists between two negative charges, but not between two opposite charges. So we know for a fact that you can't have electric field strength as 0. And when you have like charges, so let's say you've got two positive charges, the field lines for this positive charge would be away from that positive, and this one would also be away. So they're in opposite direction. They're both pointing away from each other. For two negatives, the field lines would be towards the negatives. At the end of the day, they'll still be in opposite direction. So the electric field strength will not be 0 because the fields are in the same direction. The electric field strength, obviously write that down, will not be 0 because the fields are in the same direction. Next part 3 says an electron is positioned at point X, equidistant from both P and Q. On figure 4.2, draw an arrow to represent the direction of the resultant force acting on the electron. Now we've got our 4 nanocoulomb charge here, and we've got our minus 7.2 nanocoulomb charge here. And we've got our negative electron, a negatively charged electron at this point. Now this minus 7.2 nanocoulomb would repel it and would apply a force in this direction. The 4 nanocoulomb charge would attract it and it would apply a force in this direction. So the resultant force would lie somewhere in between. Now because the minus 7.2 nanocoulomb would apply a repulsive force that's greater in magnitude than the 4 nanocoulomb attractive force. The resultant would be closer to the red arrow that we've drawn here. So somewhere along this line, this is where the resultant force would act. Let's erase the other two arrows. Here we go. Question 5 says the variation with potential difference V of the charge Q on one of the plates of a capacitor is shown in figure 5.1. So we've got the charge Q 10 to the power minus 4 coulombs, and we've got the potential on the x-axis. The capacitor is now connected to an 8 volt power supply and two resistors R and S as shown in figure 5.2. So we've got our capacitor, and this capacitor is connected to a resistor and a power supply, and there's another resistor over here, 220 kilo ohms, 25 kilo ohms. The switch can be in either position X or position Y. So when the switch is in position X, the capacitor is in charging mode. Current flows through the resistor, goes to the capacitor charges. When the switch is connected to Y, the capacitor discharges across this resistor S. The switch is in position X so that the capacitor is fully charged. Calculate the energy E stored in the capacitor. Now, to find out the energy stored in a capacitor, given that we have a charge and voltage graph, we can either find the area under the graph, or we can use the formula half QV. Half, let's go back to our graph. The battery has an EMF of 8 volts, and at that 8 volts, at this 8 volts, the charge that's stored in the capacitor is 1.2 into 10 to the power minus 4 coulombs. So this is what we'll use. Half into 1.2 into 10 raised to the power minus 4 times 8. And the energy that we get is 4.8 into 10 raised to the power minus 4 joules. The switch is now moved to position Y. Show that the time constant of the discharge circuit is 3.3 seconds. Now the time constant tau is equal to RC. When it's moved to position Y, when the switch is connected in this position, the resistor that is part of the circuit is 220 kilo ohms, and the capacitor has some capacitance, which is not given in the question, but we can still find it out. So the resistance is 220 kilo ohms times the capacitance. The gradient C is equals to Q over V. So the gradient of that line, or basically not exactly the gradient, it's ratio, but since it passes through the origin, you'll get the same answer. So Q upon V gives you capacitance. Q is 1.2 into 10 raised to the power minus 4, and the potential at that point is 8 volts. The capacitance that we get is 1.5 into 10 raised to the power minus 5 farads. The time constant is 3.3 seconds. Part 2 of the question says the fully charged capacitor in A stores energy E. Determine the time taken for the stored energy to decrease from E to E by 9. Now, when the energy decreases, what also decreases along with that energy is the potential difference across that capacitor. And it follows the equation V is equals to V naught e to the power minus t over RC, or tau. RC, the time constant. Now we just need to figure out what would the potential be after the energy becomes E by 9 from E. We know that energy is proportional to V squared. By the equation, E is equals to half CV squared. Half is a constant, C is a constant, E is proportional to V squared. So when energy becomes 1/9 the original value, the potential, because of the squared sign, becomes 1/3 of the original value. So the potential becomes V naught by 3 given that the starting potential is V naught, e to the power minus t over 3.3. V naught cancels out with V naught. We'll add ln to both sides of the equation. This gives us minus t over 3.3 into ln e. Ln e is equal to 1. Solving for t, we get 3.6 seconds. Part C of the question says a second identical capacitor is connected in parallel with the first capacitor. So we've got our original circuit here. If we add a second capacitor here parallel to the original capacitor, stated explain the change, if any, to the time constant of the discharge circuit. The time constant tau, which is equals to RC. Now the resistance does not change, but what changes is the capacitance. When we have two capacitors in parallel, and because they're identical, the total capacitance double. We simply add the capacitance of each capacitor. So the total capacitance doubles. And because the total capacitance doubles, the time constant also doubles. Time constant is doubled. Question number 6 says a small solenoid of area of cross section 1.6 into 10 to the power minus 3 meters squared is placed inside a larger solenoid of areas of cross section 6.4 into 10 to the power minus 3 meters squared as shown. The larger solenoid has 600 turns and is attached to a DC power supply to create a magnetic field. The smaller solenoid has 3000 turns. Compare the magnetic flux in the two solenoids. Now magnetic flux is BA, magnetic flux density times the cross sectional area. Since the larger solenoid has a larger cross-sectional area, it will have a greater magnetic flux. So greater or more flux in the larger solenoid, or you can say lesser flux in the smaller solenoid. Part B says compare the magnetic flux linkage in the two solenoids. Phi is equals to BAN. Now, for that you need to find out the product of the cross-sectional area and the number of turns. You realize that the product comes out to be greater for the smaller solenoid. So this time around, the flux linkage will be greater in the smaller solenoid. C part 1 says state Lenz's law of electromagnetic induction. Lenz's law of electromagnetic induction states that the direction of induced EMF is such that it opposes the change that produces it. Part 2 says the terminals of the smaller solenoid are connected together. The smaller solenoid is then removed from inside the larger solenoid. With the reference to the magnetic fields, explain why forces needed to remove the smaller solenoid. Now, when we connect the terminals of the smaller solenoid, and when we try to remove it, the smaller solenoid experiences a change in magnetic flux linkage as it moves away. Because it experiences a change in magnetic flux linkage, that induces an EMF causing a current to flow in the smaller solenoid. And that will cause magnetic poles to be created. And the magnetic poles would be such that they oppose the change that produce it, as we just stated according to Lenz's law. So that will result in an attractive force, which will prevent it from moving out. So this is what we write. change in magnetic flux linkage in the smaller solenoid induces an EMF causing current to flow. This produces a magnetic field such that the poles of the two solenoid attract each other.